Ever wondered why a simple stir in a stainless Euro steel pot produces that unmistakable clink? In the next few minutes we Eurostrade LL trace that sound from the moment your spoon hits metal to the way it travels through air, revealing the physics hidden in everyday cooking. When a stainless steel pot is lifted from the stove, its surface vibrates and emits a sharp clink that travels through the kitchen air. The vibration originates at the point where the pot's rim contacts the heat source, creating a localized disturbance in the metal lattice. This disturbance propagates as longitudinal waves along the pot's walls, causing the entire surface to oscillate at a characteristic frequency. The frequency is determined by the pot's dimensions and material stiffness. Thinner pots tend to vibrate faster than thicker ones. When the oscillation reaches the air, it compresses and rarefies the surrounding molecules, producing a pressure wave that we perceive as sound in our immediate environment. The sharpness of the clink is due to the high amplitude of the initial vibration, which quickly decays as energy dissipates into heat and air. Because stainless steel has a low internal friction coefficient, it transmits vibrations efficiently before they lose coherence. The waveform overlay in the visual demonstrates how the clink's amplitude peaks and then falls off, illustrating the transient nature of kitchen acoustics. By observing these patterns, students can link everyday sounds to underlying physical principles, such as resonance, damping, and wave propagation. Thus, the humble clink becomes a tangible example of how matter, motion, and energy interact in our daily environment. Pause 0.8. When a spoon or whisk is inserted into a liquid-filled metal pot, the fluid exerts Euros varying forces on the Eurostrade's inner surface. These forces are not constant. They fluctuate as the stirring motion accelerates and decelerates, creating a periodic pressure pattern that travels along the rim. The metal rim responds by undergoing two primary mechanical motions: shear deformation, where adjacent layers slide past one another, and flexural bending, where the rim arches upward or downward. Shear modes are driven by tangential stresses generated by the swirling liquid, while flexural modes arise from radial pressure differences that push the rim outward and inward. Because metal has a high elastic modulus, these deformations propagate as standing waves whose frequencies depend on the Eurostrade's geometry, thickness, and material density. When the natural frequency of a shear or flexural mode matches the stirring frequency, resonance occurs, amplifying the vibration amplitude and making the clink audible. The vibrating rim launches compressional sound waves into the surrounding air. The acoustic pressure oscillates at the same frequency as the mechanical vibration. The perceived pitch of the clink is therefore a direct manifestation of the Eurostrade's resonant shear or flexural mode, not merely the spoon Eurostrade's motion alone. By altering the stirring speed or changing the Eurostrade's rim thickness, one can shift the resonant frequency and thus modify the sound Eurostrade's timbre in predictable ways. This mechanistic link between fluid dynamics, solid mechanics, and acoustics explains why a simple stir can produce such a distinct metallic note. Pause 0.8. When a spoon stirs a pot, the metal surface vibrates at frequencies set by the stirring speed and the Eurostrade's material. These mechanical oscillations push adjacent air molecules into alternating compressions and rarefactions that travel outward as sound waves. Because the pot is a rigid body, most of its vibrational energy couples efficiently into the surrounding air rather than dissipating internally. The amplitude of each wave depends on how much kinetic energy the spoon transfers to the metal rim during every stir stroke. As waves propagate, they interfere constructively and destructively, creating a complex pattern that our ears interpret as a clink. A decibel meter placed near the pot records these pressure fluctuations in real Euros time, displaying values that rise with faster stirring. The 3A circumflex Euros D animation shows concentric wavefronts expanding from the Eurostrade's surface into the kitchen air, illustrating uniform energy spread. Each shell in the animation represents a snapshot of the same oscillation phase, highlighting how sound energy radiates isotropically. The speed at which these shells move is governed by the medium Eurostrade's acoustic impedance and remains constant for a given temperature. By observing the meter Eurostrade's spikes, one can correlate specific stirring motions with distinct pressure peaks in the recorded waveform. Thus, the clink we hear is a direct mechanical Euros acoustic conversion that follows simple physical principles. This mechanism first view shows how everyday kitchen sounds arise from fundamental wave physics without invoking complex chemistry. Pause 0.8. When a spoon strikes the rim of a stainless steel pot, the impact generates vibrations that travel through the metal and into the air. These vibrations, are mechanical waves, whose amplitude is small but whose frequency content can be captured by a microphone positioned just above the surface. When we perform a Fourier transform on the recorded signal, the result appears as a spectrogram that displays intensity versus time and frequency. In the case of a clink, two prominent peaks emerge near 400 Hz and 800 Hz, indicating strong harmonic components. The lower peak corresponds roughly to the fundamental frequency of the pot's first flexural mode, while the higher one is its second overtone. Because stainless steel has a high elastic modulus and low internal damping, these modes persist long enough to be clearly resolved in the spectrum. If we map each frequency to its nearest equal tempered musical note, 400 Hz aligns with roughly D4 and 800 Hz with A5. Thus the clink produces a short burst that sounds like two notes played simultaneously, a sonic fingerprint of the pot's geometry. By comparing spectra from pots of different sizes or materials, we can observe systematic shifts in peak frequencies. Larger vessels exhibit lower fundamental peaks because their longer dimensions reduce the stiffness per unit mass. Conversely, a pot made of aluminum will show higher frequencies due to its lighter density and softer modulus. This simple acoustic experiment demonstrates how everyday kitchen sounds encode physical properties that can be decoded with basic signal processing tools. Pause 0.8. When you stir a pot, the metal surface begins to vibrate, converting kinetic energy from your spoon into audible sound waves. The frequency of those waves depends on the pot's material density and stiffness, which determine how quickly it can flex. Steel, with its higher modulus, resists deformation more than aluminum, so it produces a sharper, high-frequency clink. Aluminum's lower density allows the walls to flex more easily, yielding a deeper, resonant tone that lingers longer. Pot thickness adds another layer of control. Thicker walls dampen vibrations, reducing peak amplitude and shortening the decay time. A thin saucepan will let sound travel faster through its material, creating a bright, ringing quality that fades quickly. Conversely, a thick stock pot absorbs more energy, so the clink is muted and the sound stays within the vessel longer. The liquid level inside also shapes the acoustic signature. Water acts as an additional mass that lowers resonant frequency. A pot filled to half capacity will produce a lower, fuller tone than an empty one, because the liquid's inertia resists rapid motion. When the water level is high, the sound becomes muffled. The liquid dampens surface vibrations and absorbs high-frequency energy. By measuring peak amplitudes with a microphone, we can quantify how material, thickness, and liquid level influence the clink's loudness. Plotting these values side by side reveals clear trends that help chefs choose cookware for optimal auditory feedback. Pause 0.8. Begin by selecting a saucepan that feels solid and has a flat bottom. The material will influence how vibrations travel through it. Place the pot on a stable surface and fill it with water to about halfway, ensuring the liquid level is consistent for each trial. Hold a spoon in your hand and stir the water in a steady circular motion. The spoon a Eurostrade S contact point will generate a series of impacts against the pot rim. Simultaneously, position your smartphone mic approximately 10 centimeters from the pot to capture the acoustic signal without introducing excessive ambient noise. Press record on the phone and let the stirring continue for 30 seconds. This duration balances sufficient data with viewer engagement. After recording, transfer the audio file to a computer and open it in an audio editing program that displays waveforms. Zoom into the waveform to identify repeating peaks that correspond to each spoon impact. These peaks form the visual representation of the clink. Measure the time interval between successive peaks using the software Eurostrade S roller tool, and calculate the frequency by taking the reciprocal of this period. Repeat the experiment with different pot materials such as stainless steel, aluminum, or ceramic to observe how each alters the clink Eurostrade S pitch and decay. Finally, compare your measured frequencies to known resonant frequencies of common kitchen utensils. This comparison reveals the underlying physics behind everyday sounds. Pause 0.8. We began by defining the kitchen clink as an everyday acoustic event. We then explored how stirring creates mechanical vibrations in metal pots, which couple into air as pressure waves. The spectral analysis revealed discrete peaks at around 400 A circumflex euros HC and 800 A circumflex euros HSI euros musical notes that give the clink its character. Finally, we examined how material properties, geometry, liquid level, and temperature shift these resonances, showing that even small kitchen variables shape the sound we hear.